Today we're going to start the second half of Calculus 1 of your first year calculus course. We spent the first half of calculus dealing with differentiation, or the process of finding derivatives and their applications, that instantaneous rate of change. The second half of calculus is going to be kind of the opposite of that, and some application of the opposite of that. It's going to be called integration, or finding the value of integrals, which is basically anti-differentiating or anti-deriving, or going backwards. So, starting today, or this unit, or this section, is going to be indefinite integration. There's definite integration, and there's indefinite integration. You can have a definite integral or an indefinite integral. We're going to start with indefinite integrals, or indefinite integration. And it's a process of finding antiderivatives. If f of x, if lowercase f of x is a function, capital F of x is an antiderivative. And there's some varies on this notation, so I'm going to kind of give you different ways that you might see it, but it all means the same thing. So we're going to get an example. If little f of x equals 2x, what is big F of x, or capital F of x? Or another way they might say it is, if capital F prime of x equals 2x. So it's saying, if the derivative of this, of f of x, of capital F of x is 2x, find the original f of x, the big F of x. So what it's asking is, what is the original function? If this is a derivative, if 2x is a derivative, what's the original function? Or what function has a derivative of 2x? It's kind of easy when you know that the derivative of x squared gives you 2x. So capital F of x is x squared. The antiderivative of 2x is x squared. You're going up. You're going up one instead of down one. You're anti-deriving, so you're going up. To show you an example of something that's very important when anti-deriving, we're going to derive these three functions, these three expressions, and we're going to see what happens here. 10x squared plus 4x minus 1, the derivative of that is 20x plus 4. X to the 8th plus 5, the derivative of that is 8x to the 7th. Cotan of x plus 14, the derivative of that is negative cosecant squared of x. If you notice in each one of these, when you derive, the constant goes away. The constant disappears. The derivative of a constant is 0. When you anti-derive, if I anti-derive this, any constant could have been there to begin with. It didn't have to be a minus 1. There could have been any constant there to start. This could have been 10x squared plus 4x plus 100. The derivative still would have been 20x plus 4. Okay? No matter what that constant is, when you derive it, it goes away. So when you anti-derive it, you have to account for the fact that there could have been a constant at the end of the original function. And now we're going to talk about our notation, our symbols that indicate to us that we need to anti-derive, and some vocabulary involved with that. A differential equation. A differential equation is an equation that involves x's and y's and derivatives of y. So an example would be y prime equals 3x squared. It doesn't have to have both x's and y's, but it does have to have a derivative of y in there somewhere, or a derivative of whatever variable you're deriving with respect to. So you get y prime equals 3x squared. It can also be written as dy dx equals 3x squared, since that's equivalent notation. An indefinite integral, or a general antiderivative. These are functions whose derivative give the new function, or give the given function that you're integrating or anti-deriving. So you're looking for the original function. Notice this is plural. Function 2, meaning that constant at the end could be anything. So it's not just one function, it's one family of functions with a constant at the end. The first part's always the same, but the constant could change. So, we write dy dx equals f of x, little f of x. dy dx, the derivative is this function here, this expression. Well, we multiply both sides by dx, and you get dy equals f of x dx. This is the more standard notation that you'll have to become familiar with. Now, in order to integrate, in order to anti-derive, you need the integral symbol, the integral sign, which is this little curvy sign right here. Just like a radical sign tells you to take the square root of something, An integral sign tells you to integrate or antiderive. Well, if you integrate dy, you're left with y equals. So your new function, your new function here, y, your original function is going to be the integral of f of x dx. And that's going to equal capital F of x plus c. That c stands for that family of functions, that family of constants, that unlimited number of constants. Any number could be at the end. Plus 1, minus 7, plus a billion, plus 0. Any number could be at the end. So that's why this is a family of antiderivatives, or a set of antiderivatives, because this c could be anything. In this notation here, this is the more common, the formal notation symbols you're going to be seeing. The little squiggle's your integral sign, and all this has to be here. You usually don't see the y equals, usually you'll just see the integral sign. The function itself, whatever that original function they're talking about is, what you're antideriving, that's called the integrand. And then you have your dx at the end, that's your variable of integration. Similar to when we were doing implicit differentiation, where we would be deriving dy dx, or dx dt, dy dt, dv dt. All right? Eventually, we will get to antideriving with more than one variable here. So this dx at the end is very important to keep there. A lot of students will leave that out when they're writing and going through their practice problems when they first learn this. But it's very, very important to make sure you throw your dx after your integral, so you know what you're deriving or antideriving with respect to. So that antiderivative is f of x, which is an antiderivative, plus c, your constant of integration. Never forget your plus c. Always add your plus c at the end, so you realize, or you represent, that any number could go on the end and you'd still have the same derivative. So that these are all a bunch of antiderivatives. All right, we're going to go over, review real quick, the power rule for deriving, and then we'll bring that into a power rule for anti-deriving. So your power rule for deriving, if I had y equals x to the fifth, I would bring the 5 down and multiply by the power. Then I would subtract 1 from that power, so it would be y prime, the derivative, equals 5x to the fourth. Multiply by the power, subtract 1 from the power. Well, when you antiderive, you're going to go the exact opposite. If I want to go from here to antiderive it back to here, instead of subtracting 1 from the power, I would now add 1 to the power. Then instead of multiplying by the power, multiplying by the original power, I'm going to divide by the new power. Because you're always multiplying by the higher power, the original power, so you want to divide by your new power. After you add 1, you divide by that new number. And then with the power rule for integration, we always have to make sure you add the c at the end. So y prime equals 10x to the ninth. I want to add 1. So 9 plus 1 is 10. Then I want to divide by the new power. Divide this whole thing by 10. So I would get 9 plus 1, whole thing, over 10. 10's cancel out, so I'm left with x to the 10th. So y, the original, the antiderivative, is x to the 10th, and I have to add c, plus c at the end for that set of constants. We're going to walk through a couple of them here, so you see what it looks like. I have 8x to the 7th. I want the integral of 8x to the 7th with respect to x. I want to antiderive this. So I'm going to add 1 to this power. So it becomes x to the 8th. I want to divide the whole thing by the new power. 8 over 8 goes, so I'm left with x to the 8th. Then don't forget, add your c, plus c. So there's your antiderivative of 8x to the 7th with respect to x. The integral of 4x squared with respect to x. I'm going to add 1 to the power, so I know I'm going to get an x cubed. Go up. Now I'm going to divide by the new power. The 4 and the 3 don't cancel, so I'm left with 4 thirds x cubed, and again, add c. Finally, x to the 5th. I want to add a power, so I know I'm going to get x to the 6th. Divide by your new power is going to be over 6, so you can either write this as 1/6 x to the 6th, plus c, or x to the 6 over 6 plus c. Either way. Now in integrating, there is no product rule for integration. There is no quotient rule for integration. There are a couple other rules, but for the most part, all of your anti-deriving will come from powers. X to a power, or a coefficient, x to a power. You always want to write it as something times x to a power. Positive power, negative power, fractional power, doesn't matter. But you want to rewrite your original equation, the one you're trying to anti-derive, that integrand, as a power of x before you anti-derive it. You can't leave it as a fraction. You can't leave it as a product of two things. So for example here, the integral of 1 over x to the 7th with respect to x. Well, I want to write that as a power of x. So I rewrite that as the integral of x to the negative 7th dx. And when I anti-derive this, again, add a power. So x to the negative 7 plus 1 is x to the negative 6. Divide by your new power. Divided by negative 6 plus c. More than likely, you would rewrite this as negative 1 over 6x to the 6 plus c. Usually don't write it with the negative exponents. Same thing with a radical here. Want to rewrite the integral of square root of x with respect to x as x to a power in your integrand. So the integral of x to the 1/2 dx. So again, when we integrate this, add a power, so it becomes x to the 3/2. Divide by your new power. Divide by 3/2. Add your constant at the end. Obviously, we're going to clean this up a little bit. Dividing by 3/2 is the same as multiplying by its reciprocal. So this equals 2/3 x to the 3/2 plus c, plus any constant we want to throw there. Integrating trig functions. You really have to know your derivatives of your trig functions in order to anti-derive trig function. You got to be careful with your sign here, with a positive or negative. Half the trig derivatives give you a negative value, half the trig derivative gives you a positive value. Remember the c's, cosine, cotan, cosecant, that when they're derived, they always give you a negative value. The integral of cosine of x dx. It wants to know what function has a derivative that is cosine of x. So the integral of cosine of x dx is sine of x plus c. So any constant could be on any of its trig function. Now realize when you anti-derive a c term, your antiderivative is not going to be negative. It's only when you derive a c term. Obviously, unless there's a negative constant out in the front. But for now, if you anti-derive cosine of x, you want to get the sine of x plus c. The derivative of sine is cosine. Now the antiderivative of sine of x with respect to x. Well, what has a derivative of sine? Well, cosine gives a derivative of negative sine. So I want a negative cosine to get rid of that integral. So negative cosine of x plus c. When you derive negative cosine of x, you get negative sine of x. So those two negatives would cancel, and your constant goes away. And like I said, you need to know your trig derivatives. So if you see something that's sectan, or something can be rewritten as sectan, you know the antiderivative of secant of x tan of x with respect to x is secant of x plus c. The integral of cosecant squared of x with respect to x. Well, what has the derivative of cosecant squared? Well, cotangent has the derivative of negative cosecant squared, so I must be looking for negative cotangent of x plus c, plus some constant. Some integrations that sometimes trick people. Two up here, and then one we're going to walk through a little bit. The integral of 7 dx. Well, this wants to know what function has a derivative that gives you 7. Well, there is no x there, so you can think of it as x to the 0 if you wanted to, but you know that if you have a constant, the antiderivative must be a linear function, must be something x. So the antiderivative of 7 with respect to x is 7x plus c. The derivative of this would be just 7. The antiderivative of dx, nothing there, it's just like a 1. Some people get a little confused when they just see a dx, they're not sure if it's trying to trick them or not. It's not, it's just like the antiderivative of dx. The antiderivative of 1 dx would just be an x plus c. Something to note here, if this said the integral of dt, for example, they gave you a different variable than x, this would be t plus c. So make sure you do pay attention to what variable they tell you, so you write the proper thing down and you get the full credit. You don't lose any points on your assignments or for notation purposes. Now you get this one here. 3x squared minus x plus 1 all over radical x, all over the square root of x, the integral of that integrand with respect to x. I told you before, there is no product rule, there is no quotient rule for antideriving. You have to get it as a string of powers of x, x to the something, or something x to the something else x to the something, plus or minus something else x to the something. Everything has to be x to a power, and it can have a constant or a coefficient out front. So I took this and I broke it down. I divided every term by the denominator. Integral of 3x squared over radical x minus x over radical x plus 1 over radical x with respect to x. Then you got to simplify these. X squared over the square root of x. Well, x is on the top and the bottom. You subtract the powers. So it becomes 3 x to the 2 minus 1 half, x to the 3 halves. Minus x to the first over x to the 1 half becomes minus x to the 1 half, plus 1 over x to the, 1 over the square root of x is x to the negative 1 half, because x on the bottom. So you get integral 3x to the 3 halves minus x to the 1 half plus x to the negative 1 half with respect to x. Something power of x, something power of x, something power of x. Now you can antiderive using that power rule. Add a power, divide by the power. I would suggest right now you pause this, try to find this on your own, then watch as I do it in a second. Okay. 3x to the 3 halves, add a power. 3 halves plus 1 is 5 halves, so I'm going to get x to the 5 halves. I'm going to have 3x to the 5 halves divided by 5 halves. Add a power, divide by the new power. Minus x to the 3 halves over 3 halves. 1 half plus 1 is 3 halves. Plus x, negative 1 half plus 1 is positive 1 half over 1 half. And again, don't forget your constant at the end. That's a little slanted there, but we'll figure it out. We want to clean up these coefficients here, and then we'll be good for antiderivative. Dividing by 5 halves is like multiplying by 2/5. So 3 times 2/5 would be 6/5 x to the 5 halves minus dividing by 3 halves like times by 2/3, so you get 2/3 x to the 3 halves plus dividing by 1 half is like multiplying by 2, 2 x to the 1 half plus c. Sorry that looks a little ugly, but if you need to, rewind it and listen to me walk you through again. But there you go. The antiderivative of this quotient is this long polynomial. All right, so they were general antiderivatives, indefinite integrals. They all have to deal with some family of functions, an antiderivative of a function itself, plus some constant at the end. Well, there are going to be some times where problems or examples want a specific antiderivative, meaning you could throw any constant at us, and this would be the antiderivative. But we want a specific antiderivative. Well, if they give you that, they have to give you a specific starting point, some kind of initial condition. So these are initial conditions in particular specific solution problems. They'll tell you maybe this will be how you see it. Solve the differential equation. So they want the answer. They want the antiderivative. Capital F prime of x equals 3x squared minus 1. So there's your initial, original function, the one you want to antiderive. And they're going to tell you capital F of 2 is 4. So they give you the derivative of capital F. So here's your derivative. And they tell you the value of the function itself at 2 is 4. So, a general solution will give you the C. So to find your first step, find your general solution. Add a power, divide by a power. X to the x squared plus 1 is x to the third. Divide by 3, so this is x cubed minus 1x, and then your plus C at the end. But they don't want a general solution. They want the value of f, capital F, that goes through this point, 2, 4. So when they give you initial condition, you've got to find a specific solution. So you have another step. Here is a family of functions that all start with x cubed minus x, and then you have different constants. I have x cubed minus x minus 4, x cubed minus x minus 3, x cubed minus x minus 2, minus 1, 0 there, x cubed minus x plus 1, x cubed minus x plus 2, x cubed minus x plus 3, x cubed minus x plus 4. So you see all these functions are exactly the same. They're the same function, they're just moved up or down. So the derivative is always the same. That's why I had the same differential equation that represented these. But we want the specific solution such that f of 2 equals 4, meaning when x is 2, y is 4. So we're looking for this curve here. So we're going to go using our general antiderivative. We have our initial differential equation, 3x squared minus 1, our initial condition, capital F of 2 equals 4, and our antiderivative, our general antiderivative. Well, now in order to find the specific solution, we need to find the value of C. That's what they're looking for. What constant are you adding on the end so that your curve goes through this point, so that your curve satisfies this initial condition? So you're going to say, well, when x is 2, f of x should be 4. So 4 should equal 2 cubed minus 2 plus C. And from here it's just quick little algebra. 8 minus 2 is 6. 4 equals 6 plus C, so C must equal negative 2. So your function that satisfied that initial condition with this differential equation, with that as its derivative, was x cubed minus x minus 2. And if we go back and look at that, x cubed minus x minus 2 was this one here that went through negative 2. And if you trace it up, that was the one that went through the point that we were looking